Have you ever wondered why your fancy travel mug keeps your coffee steaming hot for ages, while a normal mug gets cold in like 10 minutes? Well, it's all down to one word: insulation. And today, we're going to unpack the physics behind it by breaking down a really cool science experiment. So, let's dive right in and see how it works.
All right, take a look at this. This is our setup. It's pretty simple, right? We've got a metal can full of hot water, a lid to stop evaporation, a thermometer, and of course, some kind of insulation wrapped around it. The whole point of this is to figure out which material is the absolute best at keeping that heat locked in. We're going to tackle this like a real scientist, taking it one logical step at a time.
You know, any good experiment has to have a solid plan. And the very first thing you've got to do is figure out what you're changing and what you're measuring. This is like the absolute foundation of a fair scientific test.
So, let's kick things off with a key question. In this whole setup, what is the one thing that the student is changing on purpose to see what happens? Go on, have a little think about it.
Just so we're all on the same page, the independent variable is basically the cause in a cause and effect relationship. It's the thing we control, the thing we change. And a super important rule in experiments is that you should only ever have one of these.
And the answer is the type of insulating material. That's it. We know this because the method literally says the student repeats the experiment using the same thickness of different insulating materials. See, that's the one and only thing they're swapping out each time.
Okay, so if changing the material is our cause, what's the effect? What is the student actually measuring to see the results of that change? This, my friends, is our dependent variable.
Yeah, the name kind of gives it away, right? The dependent variable depends on the independent one. It's the result. It's the data that we're writing down, the thing we're watching like a hawk to see if it changes.
And in this case, the dependent variable is time. More specifically, the student is measuring the time it takes for the water's temperature to drop by a certain amount. This little measurement is going to tell us everything we need to know about how good each insulator is.
Right, so we know what we're testing and what we're measuring. Now we got to think about our tools. Because in science, picking the right instrument for the job is absolutely critical if you want results you can actually trust.
Okay, so the student has a choice to make. We've got thermometer A, your classic old-school liquid thermometer, and thermometer B, a nice modern digital one. Now, the big difference here is all about precision. If you were running this experiment, which one would you pick?
Let's zoom in on the digital one for a second, thermometer B. A really important feature of any measuring tool is its resolution. So looking at that screen, what's the smallest possible change in temperature that this thing can actually show us?
So, what is resolution? Well, it's all about the level of detail you can get. Think of it like a camera. More pixels give you a sharper image. Here, a smaller resolution means a more precise, more detailed measurement, which is almost always what we want.
And the answer is 0.1 degrees Celsius. You can see it right there on the display. It shows 1 decimal place. That means it can spot changes as tiny as 1/10 of a degree. Now that's pretty precise.
Okay, so we know the digital one is super precise, but what's the deal with the analog one? Why is thermometer A, the one on the left, so much trickier to use and so much more likely to give you a dodgy reading?
Well, there are actually a few good reasons. For starters, the little red line might land somewhere between 2 marks on the scale, which means you'd have to guess. Plus, the scale itself might just be hard to read. But the big one is something called parallax error. That's where the reading looks different depending on the angle you're looking at it from. All of these things can mess up your data.
All right, we've nailed down the method and the tools. Now it's time to get our hands dirty with some calculations. Physics isn't just about big ideas. It's about using math to figure out exactly what's going on. So we're told that 10,500 joules of energy left the water as it cooled down by 20 degrees Celsius. We're also given a special number for water called the specific heat capacity. We start with our main equation, but we need to find the mass m, so we just shuffle the equation around a bit. Now for the easy part, we just plug in the numbers we know. 10,500 divided by 4,200 times 20. Pop that in a calculator and boom, we get an answer of 0.125 kilograms. It's a perfect example of how an equation can help us find something we couldn't measure directly.
Okay, the experiment is done, the math is finished, we're on the home stretch. This is maybe the most important part, looking at our results and figuring out what they're actually telling us. What's the story here?
So here it is, the data for 2 of the materials they tested, material X and material Y. The table shows how many seconds it took for the water to cool down by 20 degrees with each one. Just take a second and look at those numbers. What do you see? Let's break this down. For material Y, it took a whopping 745 seconds to cool down. But for material X, it only took 450 seconds. So a longer cooling time means the heat is escaping way more slowly. That makes material Y the better insulator, hands down. And in physics speak, we'd say it has a lower thermal conductivity.
So the main takeaway here is really simple. Material Y is the winner. It's the better insulator because it kept the water warmer for longer, and this tells us it has a lower thermal conductivity. Simple as that.
So there you have it. We've totally unpacked this investigation, from setting up the variables all the way to the final conclusion. But, science never really stops. So I'll leave you with this question. Now that you know all this, how could you use these ideas to design an even better, even more accurate experiment? That's something to chew on.